Hello students, welcome back. In this video, we're going to fix a big problem with NovaStrike. Right now, our game is going to essentially run slower on slow computers, and it's going to run faster on fast computers. So what does this mean? Well, our bullets will fire at a faster rate on fast computers and slower on slower computers. Our stars will move faster on fast computers, slower on slow computers. And this is all because everything that we are processing right now is in terms of frames. We know that draw function from the P5 library will run every single frame of our game. And so if our computer is running at, say, 60 frames a second, well, then it's going to process that thing 60 times in 1 second. And if our computer is only running 30 frames per second, well, then it's going to process it 30 times in a second. And our game is going to be half as slow, half as fast. So this is bad. This is inconsistent gameplay, and we don't want inconsistent gameplay. We want the same experience on every single computer. So what we need to do is switch from a frame-based system into a time-based system, because time is experienced the same on slow computers or fast computers. 1 second or 2 seconds or 3 seconds of time is the same time interval on a slow computer and on a fast computer. So we're going to switch from frames to time. And once we do that, that's going to open up the doors for us. Because if we think about our game, as we play our game, the longer we play our game, as time goes on and on and on, we want our game to scale up in difficulty. It needs to get harder and harder and harder. That's what makes it fun. So we're going to use our new representation of time to build a difficulty ramp, something that just gradually increases in difficulty. So the longer we play our game, the harder it gets. So let's head to the computer screen and then let's dive into this lesson on time and difficulty ramps. So I have lesson 5's starter file open here in vscode.dev. I'm going to minimize this file for a second and go to my NovaStrike folder and open lesson 5 directly in the browser so we can see what we're working with. All right, here we go. NovaStrike. What do we got? Whoa! Hey now. We are at ludicrous speed. Those stars are going crazy. How about my bullets? Okay, I can't even fire anymore. My bombs don't go away. And my player is just zooming all over. I can't control him. So it almost seems like every single system that we had in place for, updating our game is completely broken. And it's because those systems all were written in frame-based motion. And now we are switching to a time-based system. So everything's broken. Stars are broken. Bombs are broken. Firing broken. Player movement. It is all broken. Boy, oh boy, do we got a lot of work to do. So let's come over to mission 1 and our mission checklist. And it says, hey, let's add the delta time variable and let's clamp it. But you know what? Before we do that, let's just scroll down and look at what we have here in the student edit zone. Because I don't know, we've added some things, but before we get to what we've added, we've changed some things. And that's extremely important. Because if you look here, our player speed, it used to be 5 pixels. 5 pixels per frame. But if we assume that we're running at 60 frames per second, to get our new speed in terms of seconds, not frames, I would take 5 pixels per frame and multiply by 60 frames per second, and I get a speed now of 300 pixels every single second. Let's look at our stars, right? We had like our minimum star speed was 1 pixel per frame. If we assume 60 frames per second, it's now 60 pixels per second. The max speed was 3 pixels per frame, assuming 60 frames per second. It's now at 180 pixels per second. So all of our values have been converted into a time-based system here. Note, we had like our cooldown frames, it was 10. Now our cooldown for firing seconds is 0.16. At 10 frames, assuming 60 frames per second, 10 divided by 60 this time gives me my 0.16. 10 divided by 60 gives me that 0.16. So all of those values have been converted. Now, let's look at how we get this dt, because all these values are dt converted. That's going to be where we find ourselves in mission number 1. Mission number 1 puts us right in the draw function. That's that P5 function that's going to get called every single frame of our game. Now, the problem is we don't want to run things every single frame. We want to run things based on a time interval, not a frame interval. So we are going to work with a variable known as delta time. This is a built-in variable, and it represents the number of milliseconds since the last frame has occurred. So the draw function runs every single frame. We basically time how long it takes, and that is the delta time variable in milliseconds. There's just one problem. We don't like milliseconds. We want to think in terms of seconds. So we're going to convert that to seconds. And in doing so, we're going to create our own version of delta time. We'll call it dt. All right. And what we're going to do is we're going to take the delta time variable, which is in milliseconds, and to convert milliseconds into seconds, we will divide by 1,000 because there's 1,000 milliseconds in 1 second. So far, so good. Now I have an accurate representation of how many seconds elapsed in one given frame on my computer. Whether it's a slow computer or a fast computer, I have it. Now, we're going to do one extra thing here. We are going to clamp that value, because if I'm playing over here, right, and I'm playing my game, and then I just go off my tab, all right, and I'm doing something, and maybe I wait like 5,000 milliseconds, and then I come back, this value is going to be really big. 5,000 milliseconds divided by 1,000, that's 5 whole seconds. dt is going to be huge, and that could like create a big jump in my gameplay. It could make some inconsistencies, and we don't want that to happen. So what we're going to do is we're going to specify a maximum value that we can use for our dt variable. And the way we do this is by calling the min function. The min function, we're going to give it 2 values, and it's going to pick the smaller of the 2 for us. So we'll say, okay, we'll start with 0.033, and then we'll pass in delta time divided by 1,000. So there's our time interval in seconds. So let's assume I'm away for 5,000 milliseconds from my game. So 5,000 divided by 1,000, that's 5 right here. And so we're going to say, hey, pick the minimum value between 0.033 and 5. Well, the minimum value is 0.033. So this is our highest value. But let's just assume that, hey, like let's assume 0.016 milliseconds have, that's our time interval. So now that is smaller than 0.033. So we're going to run that. So this is just a little safety feature we have in place to make sure we don't get crazy spikes in our gameplay. So now we have dt, the amount of time it took for one frame to elapse. And we can use that in mission number 2. Mission number 2 says update runtime using delta time. So it looks like we've got a variable here called runtime seconds. Let's go take a look at our gameplay variables. So I'm going to jump, you can stay here. I'm going to jump to this section outside of the student edit zone. We've got some new variables here. We've got runtime seconds, and it's equal to 0. So we need to track how long the game has been playing in total, right? So like we're flying our ship, and we start the game 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, etc., etc. So we have a variable here to track that, and we're going to use that total time we've played. As that time gets bigger and bigger and bigger, we are going to increase our difficulty using a difficulty ramp. And so we're going to see how to do that in coming up here in a couple of missions. But we got to make sure that we actually are increasing it. So if you think about it, what do I want to add to this? Well, right now we're adding 0. You might think, let's add 1. And that would be a bad idea, because this is happening inside of the draw function. The draw function runs every single frame of the game. So what we would be adding is 1, not every second. We'd be adding 1 every single frame. And if our game is running 60 times in a second, we would be adding 60 every single second. That would be really bad. So what we want to add is the amount of time that has elapsed in a given frame, and that is our dt variable. It's that variable we just created. So now we have an accurate measure of how long we've been playing our game in this variable runtime seconds. But then there's a second part to this mission. It says pass dt into any function that might depend on time. So I got a lot of functions in here. Update ramp values, update stars, update player, update weapon systems, update player bullets, update bomb. Let's go see what functions might need dt. So reset game to defaults, no. Generate star data, no. Spawn star, no. Okay, update stars needs access to dt. And I think that probably makes sense. That's why my star system is so broken right now. It's looking for delta time, and we're not giving it. to it. So we need to pass it in there. Update ramp values, no. Update player. Update player needs DT. Again, that system is broken. I'm moving all over the place. We don't have access to our time variable. Get input for action, no. Update weapon systems needs DT. I can't fire bullets anymore. It's because that system is broken. So we got to give that time. What else? Update player bullets needs DT. Update bomb needs DT. Okay, so a lot of those update functions need it. So if I go back up here with my up arrow to mission 2, let's pass this variable DT into the functions that need it. Update stars needed it, so I'll put DT in here. Update players needed it, DT. Update weapon system needed it, DT. Update player bullets needed it, DT. And you guessed it, update bomb needed it. So let's pass in DT. And with that, we are now sending this information about how much time elapsed in the current frame to those functions that need it, which means we can move on to mission number 3. Let's go fix some of those functions. But really, let's just see, just passing DT into some of those functions, now they have access to the information they need. Did it fix any systems? Well, stars did not get fixed. Player movement did not get fixed. Hey, but firing got fixed. I can now fire correctly. With having the correct access to the time value, we have now fixed the firing system. What about bombs? Hey, bombs fixed. Bombs got fixed. All right, so it just seems like movement and stars are still broken. So which one are we going to fix in mission 3? Looks like we're fixing update stars. So it says apply delta time to star movement. Ensure that stars move consistently across different frame rates. All right, well, this line worked absolutely perfect for us before when we were in a frame-based system. We said, hey, take the star's Y property and add to it the star's speed property. But that speed property was given in frames, right? How many pixels we were moving per frame. Now, this speed property is given to us in terms of pixels per second. So we got to do one slight change here. And to help understand what we're going to do, we're just going to write out and explain a pretty well-known quantity, a variable of motion, equation of motion. And it says speed is the change in distance over the change in time. Basically, if you want to know how fast you're going, you got to know how far you went divided by the time interval you were moving. And so I'm going to multiply this side by time, and I'll multiply this side by time. T in the denominator and the numerator will cancel, and I'm going to just flip-flop these and say, hey, if you want to know the distance you have traveled, how far you need to move, you're going to take your speed, and you're going to multiply by the time interval with which you're moving. Well, this is star.y. This is star.speed. And what is our time interval? Our time interval right here, we just pass it into our function. The time we have to move in this given frame is dt, our delta time variable in seconds. So I have to multiply my speed by dt. In doing that, the star system should be completely fixed. So let's see. Here's warp speed because we are going crazy. Now we are back. Oh, thank goodness we're back at normal speed for stars. But our ship system, our movement system is still completely broken. So we have to now fix that movement system. So let's go to mission number 4. Mission number 4. Oh, great. It finds us in update player. We knew we had to change this system, which was frame-based, and now make it time-based. So if we look here, it's a very similar concept. We have the player's X position, and we're going to set it equal to the player's horizontal speed. Remember, move direction.dx is going to either be 0, -1, or +1. We get it from our get input direction. And here it is. We're setting it to 0, -1, or +1. So then we're just multiplying it by our player's speed. The only thing we're missing here is the time interval with which we have to move. So let's multiply player.speed times dt. And this function has it because it's getting passed in right here. And let's do the exact same thing in the vertical direction now. And so with that change, our movement system for the player should be fixed. Let's check it out. Let's verify it. All right, so Nova Strike. There's our stars going at a normal speed, and now our player is back to moving the way it should. So it looks like stars are fixed, player is fixed, bullets are fixed, bombs are fixed. Damage system still looks good. We are cooking. We're right back to where we were in lesson 4, except now, instead of being frame-based, where we had inconsistencies in terms of gameplay on different machines, we have consistent gameplay because we've switched to a time-based system. This is amazing. It's so great because now we have reference to time. Let's use that time to plan for something awesome and great. And that is increased difficulty of our game. So mission number 5 finds us setting the ramp constants for our difficulty ramp system. So we are now going to put a new system into our game, our difficulty ramp, which is going to scale our game. It's going to get harder and harder and harder the longer and longer we play it. So this is a system that should have knobs or dials that we can tune and adjust. We're going to find those in our student edit zone. We passed the player system, the star system, the bullet system, the bomb system, our shield system, and now we find ourselves in mission 5 in the ramp system. The first variable is called ramp time seconds. This is a representation of how long it is going to take for our game to reach its maximum difficulty. Right now, it's set to 10 seconds. That is a very short ramp, okay? We don't want our game to reach max difficulty in 10 seconds. Come on. That would be like unfair. So I'm going to set it to say, hey, you got to play for 120 seconds to get to our maximum difficulty. If you get there, congratulations. The game will not get any harder, and your only job you have to do now is survive. So how are we going to make the game harder? Well, there's things that we have to control. We have to make the game difficulty from the beginning of the game up to 120 seconds. The first thing we'll control is enemies. So we're going to spawn enemies in our next video. This alien fleet that's going to attack us. So the first target is how many enemies we spawn at a given time. So in the beginning of our game, at the start of our game, our enemy spawn count will be 1. When it's time to spawn a wave of enemies, we're just going to spawn 1 singular enemy. But by the end of the game, when we are at our maximum difficulty at 120 seconds, when we spawn an enemy wave, there will be 4 enemies in that wave. So there is one factor we will control in our difficulty ramp. Another thing that we'll control is how quickly we spawn those enemies. So we have an enemy spawn interval. When we start, we're going to spawn those enemy waves every 2.5 seconds. And by the end of our game, at our maximum difficulty, so 120 seconds in, we're going to spawn them much, much faster. We're going to spawn them every 1.0 seconds. And the last thing that we'll control in our difficulty ramp is how quickly those enemies fire at us. At the start of our game, we're going to set our enemy fire cooldown to be some big number, like 2.25 seconds. So the enemy will fire, and then they got to wait 2.25 seconds before they can fire again. By the end of our game, at max difficulty, their cooldown will only be 0.75 seconds. So they'll fire, and now they only got to wait 3/4 of a second before they fire again, and then 3/4 of a second before they can fire again. Awesome. So our system is set. So now we just got to implement it. And so let's go to mission number 6. Mission number 6 finds us in a new function called update ramp values. And in here, we need to define our ramp value. So it says use runtime to create a ramp value between 0 and 1. So I think what we need to do first is explain a little bit of the math that we're going to use here on our difficulty ramp. So let's go back to the whiteboard here. I'm going to make this full screen and just zoom over here. And let's first start by saying a ramp is a value that is going to be between 0 and 1. So I'll say ramp is a number between 0 and 1. So maybe it's 0, maybe it's 0.25, maybe it's 0.5, maybe it's 0.67, maybe it's 0.89, or maybe it's 1.0. When it is a value of 0, when the ramp is 0, this is the start of our game. When the ramp is 1.0, this is the max difficulty of our game. According to the values that we set for our constants, this is going to be at 120 seconds. And so our ramp value will increase, and as it increases, the longer we play, as time goes on, the game gets harder and harder and harder. So as we go this way, time advances and difficulty advances. All right, so now how does that ramp actually control the difficulty? Well, imagine we made a graph, okay? We made a graph that looks something like this, zoop and zoop. And on the x-axis, we put our ramp value. And so our ramp value starts at 0, and it ends at 1. Okay, so perfect. Now on the y-axis, we are going to put something that is being controlled by the ramp. So maybe I'll put, let's do cooldown, fire cooldown. So we'll say enemy fire cooldown. So we just defined a starting value for the enemy fire cooldown. They are going to start with a cooldown of 2.25 seconds. So I'm going to put that value right here. This is 2.25 seconds. And by the end of the game, or by the end of our ramp, it's going to be all the way down to 0.75. So I'm going to put 0.75 right down here, 0.75 seconds. Now, when we start the game, remember, this is our starting point, and this is max difficulty, max diff. So at the start of our game, when the ramp is 0, our enemy cooldown and shooting is 2.25 seconds. And at the end of our game, at our max difficulty, the cooldown is all the way down here at 0.75. So I have a point here and a point here. Imagine if I drew a line connecting those 2 points, just like that. Now, we can use this line to determine what our enemy fire cooldown should be at any given point on our ramp. So let's say, remember, this is 0 seconds and this is 120 seconds. So if my ramp were 0.5, the halfway point, well, the halfway point between 0 seconds and 120 seconds is 60 seconds. I would come right up here, boop, 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 find my line, and read the value of my cooldown. So what would that cooldown be? I honestly have no idea. Maybe it would be 1.5 seconds. We wait 1.5 seconds. If we go a little bit longer, we survive a little bit more, and maybe now we're at this point, 0.89. I don't know what that time would be. Maybe it's 108 seconds. We're going to go down, doop, 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 find our value right off our line, and read the graph. And we're going to see, hey, maybe the ramp is much shorter now. Maybe we're firing every 0.92 seconds. This idea of taking our starting and ending value, drawing a line between them, and then using our ramp value to read the controlled value off of the graph is known as linear interpolation. And we are going to do linear interpolation on all 3 quantities that are going to be controlled by our ramp. Our spawn count, how many spawn in a wave, our spawn interval, how quick we spawn, and our fire cooldown. And the way we do this is with a function called lerp. So the first thing that we need to do is build this ramp, these numbers between 0 and 1, so that we can use them to create these graphs for us. So with that math in place, let's look at mission number 6. So we're going to define our ramp value. If you remember, we have a variable called ramp. In fact, let's go look at our variables here for this system. So I'm going to just jump to our gameplay variables. Here was runtime seconds. We already implemented that. And now I have 4 more variables for our gameplay variables. Ramp, which is going to be a number between 0 and 1. And then enemy spawn count. So that'll set, okay, it'll be like one enemy every time we spawn, then 2, then 3, then 4. And we'll change it based on our ramp. I have enemy spawn interval seconds. So maybe it'll start at like every 2.5 seconds, and then we'll decrease it, spawn every 2 seconds, every 1.75 seconds, every 1.4 seconds, and then we'll end it at every 1 second, every single second. And then our enemy fire cooldown, we'll do the exact same thing. So these are the variables that we are going to change based off of the ramp. So now let's create that ramp. It's currently set to 0. Well, we don't want it. We want it to be between 0 and 1. So maybe we set it to 0.5. But we don't always want to be at this point on our graph, right? We don't always want to be right here. We want to start up here, and then over time, we want to move down that value. So our ramp needs to change based on time. So we're going to use our run time seconds. We're going to say, hey, let's take run time seconds, which starts at 0, and then it goes to 1, then it goes to 2, 3 seconds, 4 seconds, 5 seconds as we play our game. And we're going to divide by our ramp time seconds, which is the time it will take for our game to reach maximum difficulty. We set it to be 120. So let's get a calculator out right here. At the start of our game, runtime seconds is 0, divided by 120 is 0. So our ramp is 0, and we start right here. Boom, that's great with a enemy fire cooldown of 2.25 seconds. Let's say we survived and we've played for 60 seconds. So now runtime seconds is 60 divided by our ramp time seconds of 120. Well, now our ramp is 0.5, so we're at our midpoint. Wonderful. And let's say we survived to 120 seconds. Well, 120 divided by 120 is 1. Our ramp would be 1, and we are at our maximum difficulty. So this is working nice. There's only one problem. If we don't die immediately at 120 seconds, we survive, and we play for another, say, 20 seconds. We get to 140 seconds divided by 120. Our ramp now is at 1.16. But I don't have a value on my x-axis for 1.16 because our starting idea was that a ramp is a number between 0 and 1. So we can't let this value get above 1, and we shouldn't let it go below 0. So what we're going to do is we will constrain this value. We'll call the constrain function around this fraction, and we'll constrain it between 0 and 1. And now our ramp is set. Excellent. With that ramp set, we can now use it to lerp, perform linear interpolation. And if you look, we are performing lerp to control enemy spawn count, lerp to control enemy spawn interval seconds. We start at our starting value for spawn count, 1 enemy per spawn, and our ending count, 4 enemies per spawn. That is going to create a nice line for us, and then our ramp value positions us on that line. Same thing with our enemy spawn interval. We start with an interval of spawning every 2.5 seconds and ending at every 1 second. And then our ramp will position us on a line between those values. And so we want to do the exact same thing now, but with our cooldown. So I'm going to take the variable that I have, enemy fire cooldown seconds, tab for autocomplete, and I'm going to set it equal to lerp. Let's do linear interpolation. But we got to give 3 values. We have to give that starting point on this graph. Where was it? We got to give this starting point right here. We also have to give this ending point right here. And then we have to give our ramp value. Where on the x-axis are we? So that we can go up. Oh, we can go up to the line that is drawn between our starting and ending point and then read off our value. So let's see how we can do that. Well, for enemy fire cooldown, I have a starting value of enemy fire cooldown seconds start. It's going to be our second value there in the list. And then our final value is enemy fire cooldown seconds end, our first value, because it's in alphabetical order. And then we'll pass in our ramp value. Perfect. And so now we are scaling not 1, not 2, but 3 values in our difficulty ramp, all involving enemies, these things that don't yet exist in our game, but we're laying the foundation to build them out nicely starting in our next video. So let's run this. If I run this now, all right, it looks exactly the same, which is super, super boring. And you can say, well, how do we know this ramp system is even working? How do we know that the difficulty is getting harder and harder and harder? Well, outside of building the entire enemy system right now, we don't. So there's something to help us, and that will be in mission number 8. Mission number 8 finds us back in Draw HUD, because we are going to draw some information to the screen. We have a ramp readout. It says display the ramp values on the screen. Show how difficulty increases over time. So it'd be very helpful to see like what is our percentage of our ramp? Are we at like 10%, 20%, 30%? How quickly are we going to spawn? What's our fire rate? All that good stuff. So if I scroll down just a little bit, I have what we'll call a debug function, draw ramp readout, where we set some text properties, we calculate some values, and then we show all of this text for the ramp value, our spawn number, our spawn interval, and our fire rate. And so this function exists already. Those instructions are written. All we have to do is call it. And we're going to call it right here in mission number 8. We'll say draw ramp readout. That's the function name, parentheses to call it, and a semicolon for good JavaScript. And now with that in there, we should get our debug information. And there it all is. If we decide we don't want it, we've tested it and we don't need it, we can just comment it out. And there it goes. It's no longer there. But we're going to keep it in because I want to see that this ramp is actually working. So I'm going to refresh my game and I'm going to hit enter. And right now my ramp is slowly increasing. And as it increases, we're going to see the spawn interval is decreasing, getting smaller and smaller and smaller. Our enemy fire rate is decreasing, getting smaller. They're going to be firing faster. So we're spawning faster. Enemies are going to spawn every 2.3 seconds. Now they're spawning every 2.25 seconds. They're going to be firing with a cooldown rate of 1.95 seconds. Right now, the enemies are going to spawn in waves of 2. And let's see, as our ramp gets bigger and bigger and bigger, what will they spawn at? probably begin spawning in waves of 3 at some point. I'm going to pause the video and let this ramp system build up, and we'll look at where our values are when the ramp system has built up. Okay, so our ramp system is now at 95% of the way there, and we're going to hit 100, and we should see all of our max values. So when our ramp is at 100%, our spawn number is 4, our interval is every single second, and our fire rate is at 0.75 seconds. Those numbers correspond exactly with what we set in mission number 5 for our ending values: a spawn count of 4, a interval of 1 second, and a cooldown of 0.75 seconds. So it looks like, according to our ramp readout, this difficulty ramp system is working flawlessly, which means this is great because our system is in place that we can now plop enemy objects right into. So when we create enemies, we have a system that will spawn the enemies for us at a faster and faster rate. The enemies will know what their fire cooldown is, and they will shoot faster and faster and faster, and will know to spawn larger and larger and larger swarms of aliens. So I can't wait to begin looking at that enemy system with you in our next video. I'll see you then.